Good morning, everybody. We can start our lecture now. Last week we have seen number systems and then lines and circles and parabolas in Cartesian coordinate system. We define what the distance in a plane is. And based on this definition, we defined circle as the set of points which has the same distance from a given point. And we have defined parabola as the set of points which has the same distance from a given point and a given horizontal line. Now we are going to start with functions and the graphs of functions. Let's first define what a function is. As you can see here, a function f from a non-empty set E to a non-empty set Y is a rule that assigns a unique value of f of x in Y for each x in D. We can pictorially show it like this. It's like a kind of a machine, where x is the input to the function, and the function creates a unique output y in the set y. It's like a machine grinding something and creating something else. Another pictorial representation is this. You have the D, that's the domain set. So D we call is the domain of the function. And there's a given x here. And f maps this x to this value, f of x, which is equal to y. There's an a here in the domain, and f maps it to f of a. The important thing here is that y should be unique for every x. I mean, the function f should not create two values of y for a given x, just one. That's another pictorial representation for the function is. I can hear my noise, I can see my noise here. Try to refresh your page if you cannot hear me. Let's continue with the function definition of function. Now let's look at some typical functions and try to assess domains and ranges. For instance, y is equal to x squared. So for every x, you get it squared and find the value of y. Now this function is defined between minus infinity plus infinity, which means the set of all real numbers. Minus infinity and infinity are not real because they are not real numbers. And as you can see, the range is between 0 and infinity because this function is always positive values. Let's look at another function, y is equal to 1 over x. This function is not defined when x is equal to 0 because a real number divided by 0 does not give you a real number. So the domain of this function between minus infinity 0, 0 is not included and 0 infinity. The range is also the same because when x is negative, y is negative 2, and x is positive, y is positive. So the range is also minus infinity and 0 union 0 infinity. Let's look at the square function. Y is equal to square root of 4 minus x. It's obvious that square root is not defined for negative values. So the domain of this function is minus infinity and 4 is included. That for this function has a value 0. For all values of x less than 4, this function is defined because negative of a negative number is positive. So the domain is minus infinity to 4. The range is again 0 infinity because we're talking about positive square root. Now let's look at this function y. That's square root of 1 minus x. Now here, absolute value of x must be less than or equal to 1, otherwise this function is not defined. This will be a negative number. So the domain of this function is between minus 1 and plus 1. Or minus 1 and plus 1 are equal. What are the values that this function can take? Well, it can take 0, it can take 1, and anything in between. So that's a closed interval. 0, 1, that's the range of this. That's the graph of a simple function, which is y is equal to x plus 2. As you can see, when x is 0, y is equal to 2. It's clear from the equation, and it's clear from this point here. When y is 0, x is equal to minus 2. So that's a line between these 2 points, passing through these 2 points. And that's the graph of the line. Let's continue. Suppose this blue curve is f of x, graph of f of x. Now, y is a measure of the height from the x-axis to the graph. So, y in a way shows the range of values of the function, shows the distance between point x and its f of x. Sometimes this could be negative, as you have seen here. Here it is positive. So it's the height of the graph about the point x is actually y. Here is more detailed graph of a function y is equal to x squared. What you basically do is you take certain points like here. Here minus 1, 1 is on the graph because when x is minus 1, y is equal to 1. Minus 2, 4 is in the graph because when x is equal to minus 2, y is equal to 2, 4 is in the graph also. So you put these points and join them in a curve. That gives you a rough idea about the graph of this function. Later on, we will investigate or study how to graph functions. Now, if you want to find a more refined graph, you can take a lot of points like here. Here, pressure is measured with respect to time in a and we have this set of points, and we can plot the graph. That be a more refined graph. Blue dots are data as you see in the previous pictures. Okay, so what you do is you try to join the points and draw a graph of pressure versus time. Let's give it a think. Let's continue. Now we have 3 figures here. First figure is x squared plus y squared is equal to 1. As we know, this is a circle centered at the origin with radius equal to 1. Now this relation is not a functional relation because as you can see, for one value of x, this gives 2 values of y. So we cannot say that this is a functional relation. However, we can do this. We set y is equal to square root of 1 minus x squared, and that's a functional relationship, and it gives us the upper semicircle. And as you can see, for each value of x, there's only one value of y. Or we can write y is equal to minus square root of 1 minus x squared. Now, in this case, you get lower semicircle, and that's a functional relationship also. Okay, let's continue with functions and graphs. Sometimes you can define functions piecewise manner. For instance, y is equal to absolute value of x. And that's a piecewise defined function by the definition of the absolute value. If x is greater than or equal to 0, the value of absolute value is equal to the x. If x is less than 0, it's a negative number, the absolute value of x is minus x. So that's a piecewise defined function with two pieces. And we can just look at the figure here for absolute value of x. Okay, y is equal to x, that's this line. For positive x, y is equal to minus x for negative x. And that's the absolute value of the function. Let's go back to the previous slide. Now you can define functions like this. Y is equal to minus x if x is less than 0. So that has a positive value. Y is equal to x squared between 0 and 1. 0 and 1 are equal. And y is equal, when x is greater than 1, y is equal to 1. So if you want to draw the graph of this function, which is piecewise defined, you'll get something like this. Okay, so that's y is equal to minus x. Okay, that's the first part of this. Between 0 and 1, it's y is equal to x squared. It behaves like a parabola. After 1, it's a constant function. Y is equal to 1 for every x which is greater than or equal to 1. So that's how you draw the graph of piecewise defined function. Join these pieces. Okay, so there is a function which is used frequently. It's called the greatest integer function or integer floor function. Now, y is equal to f of x in this case gives the greatest integer less than or equal to x. So y has integer values, okay? And that value is the greatest integer less than the given x. Let's look at the graph of this function. Okay, that's the graph of this function. Now, when x is greater than 0, less than 1, the greatest integer is 0. So that's the function. But when x is equal to 1, the graph jumps to the point. Because 1 is the greatest integer less than or equal to x. And it continues like that until at 2 it jumps here because now 2 is the greatest integer for any values of x greater than or equal to 2. And so that's how you draw this. And that's also called integer floor function. Okay, let's go back to the page defined. So that's the greatest integer floor function. Now there's the least integer function. In this case, y is equal to f of x gives the least integer, which is greater than x. So that's called integer ceiling function. Okay, let's look at the graph of this one. Okay, this is the graph of the least integer function. When x is between -1 and 0, okay? So the least integer is 0, which is greater than x. So that's how you go. Now at 0, you still have 0, but when x is greater than 0, less than 1, then 1 is the least integer, which is greater than x. And now when you move away from 1, between 1 and 2, and 2 is the least integer greater than x, and that's how you draw the graph of the least integer function. This is called the integer ceiling function. Let's go back to functions. Okay, so these are two functions that are frequently used, great integer function and least integer function. These are piecewise defined functions. Formulas for piecewise defined function, if you have a certain repetition, you can go on like this. For instance, y is equal to x if x is between 0 and 1. So this is a line starting from the origin, going up to the point 1, 1, but not equal to that point. Okay, and then you can write x minus 1. That's again a line which starts from uh, 1, 0 and goes up in values. And these will be all parallel lines, and you can give an expression like this: y is equal to f of x, where x is x minus k, for k, x between k and k, k's are integers, positive integers. So these are lines which are parallel to each other. Each starts from the x-axis and goes one unit up. Okay, these were a couple of examples for piecewise defined functions. We have seen the graphs. Now let's look at identifying functions and models. It's actually, in a way, a classification. It will give a more refined classification later on. The functions which can be expressed like this: f of x is equal to mx plus b. These are lines, m is the slope, b is the y-intercept. These are called linear functions, the general name used for the function. Now, the domain of these functions is the set of all real numbers. They are real valued functions. Functions which can be expressed as x to the power a, where a is a real constant. These are called power functions. Now, if a is greater than 0, greater than 0, then the domain is again the set of all real numbers. But a could be less than 0. That's x to the a, where a is a negative number, and that's what the meaning, 1 over x to the absolute value of a. Okay, let's look at graphs of these functions. Okay, y is equal to x is a line that passes to the origin, because when x is equal to 0, y is equal to 0. Y is equal to x, right? That's a parabola, we know that's how it's shaped. Y is equal to x cubed, that's shaped like this, because when x is negative, y is negative 2. Y is equal to x to the 4. It's similar like parabola, but it's not a parabola. It's power function power 4, and y is equal to x to the 5. That's again, since 5 is odd, this is negative, y is negative. So these are power functions. Uh, when a is negative, and this is y is equal to x to the minus 1, that's how we write it. Now, as you can see, this function is not defined at 0, whereas positive powers are defined for all real values of x. But in this case, for negative powers, you don't have this. And so that's y is equal to 1 over x. And when x is negative, you have this piece. It's not defined at 0. And as x goes to infinity, as x grows, it approaches to 0. And that's y is equal to 1 over x squared. That's how we have. So again, this is not defined x equal to 0. Now the functions which are defined as f of x is equal to a to the n, x to the n, a to the n minus 1, x to the n minus 1, and up to a1, x, and a0. These are called polynomials, as you may know from high school college. Here, ai's are the constants, real constants.
Professor,
Yes, sir.
please, your volume very low. Thank you.
It's low. How is it like now?
Now good.
Okay. These functions are called polynomials. And if an is not equal to 0, then n is called the degree of the polynomial. If n is 1, that's a linear function. If n is 2, that's a quadratic function. You know that. But the graph of polynomials can be drawn by using the roots of the polynomial, which are defined as set. So the values of x for which this is equal to 0 is called the root polynomial. In order to draw the graph of these functions, you have to know the roots. It makes graphing much easier. Okay, for instance, let's look at this one, x squared minus 2x plus 2. This has two roots. The roots are complex. Then you know that the graph of this polynomial does not cross this axis. Now for this one, x squared minus 2x plus 1, this has two roots, 1, 1. The graph of the polynomial is tangent to x-axis. It does not cross, but it touches the x-axis. If you look at this polynomial, x squared minus 2x minus 3 has two roots. That's 3 and minus 1. So it crosses the x-axis at points. Okay, here is some examples of polynomials. If you look at this, that's a third degree polynomial. All the roots of this polynomial are real. Now you know that cross the x-axis 3 times because a third degree polynomial always has 3 roots. For instance, this one, that's a fourth degree polynomial. If you find the roots of this, then you know that it crosses the x-axis 4 times, like shown here. That means this has 4 real roots. Now let's look at the last one, x minus 2 to the power of 4, x plus 1 to the power of 3 times x minus 1. So that's an 8-degree polynomial. Some roots are repeated. So you know there's a tangent here. And this crosses the x-axis at 1 here because of this rule. Minus 1 is repeated, so that's here. Of course, when you know the roots of the polynomials, you can identify the regions where the value of the function is negative and positive. So between a negative and positive values, you know that it crosses the x-axis. So it gives you a lot of idea what to do when you try to draw the graph of polynomials. Okay, another class is rational functions. Rational function is a ratio of two polynomials, p of x and q of x. Now, the domain of these functions is the set of real numbers, whole set of real numbers, except the roots of q of x. When x is a q of x, this is 0, and any real number divided by 0 is not a real number. So we know that uh, these are not included in the domain of the rational function. Let's look at an example. We will look later on such examples more, but just for the start, y is equal to 2x squared minus 3 divided by 7x plus 4. Actually, when you do a polynomial division, you have a second degree polynomial here in the numerator and a first degree polynomial in the denominator. When you divide 2x squared minus 3 by 7x 4, you get this as the result of division, and that's the remainder. Okay, that's a line. That's a line. And that's the remainder. Now you can see from here that the roots of p of x, that's the numerator polynomial, are plus or minus square of 3 over 2. And the root of q of x that only has one root, that's minus 4 over 7. Now you can just see this very easily. If x is between these values, minus square root of 3 over 2 and minus 4 over 7, when is between these two values, then you know that this is negative and this is negative, so y is positive. So both numerator and denominator are negative. You have y positive. And for minus the square root of minus of 3 over 2 and minus 4 over 7. So when you try to draw the graph of this function, you consider this. Y is less than 0 for x less than minus 3 over square root of 2, because this is now positive, q of x positive, q of x is negative, because when x is less than that, this is negative value. So here you have y is negative. Now one more thing you can say about the graph of this function, if x grows too much in the positive part, then this number here becomes smaller and smaller. And you know that your function approaches this line. Your function value is less than this line because you subtract from this line this number. However, if x goes toward minus infinity, when it comes like minus 1,000, minus 10,000, and this is positive, and your graph approaches this line again, this is not very small, so it's above this line. And when you look at the graph of this function, you will see this. This is the graph of this function. Now that red line is the line that your function gets closest to. And so when x goes to you are always below this line. When x goes to minus infinity, you are above this line. Because as you can see, okay, that's you approach this line. That line is 2 over 7 x minus 8 over 9. And so at minus 4 over 7, function is not, as you see here, this point is minus 4 over 7. So when you approach minus 4 over 7, your function grows too much because the denominator becomes very, very small. Okay? When you approach minus 4 over 7 point. So this is negative, so you go to positive. And when you approach 4 over 7 from this side, now this is positive, but that's negative here, so it's minus infinity. So that gives you a rough idea of how your function is, like this. This is another rational function, and as x goes, you have both x squares here, so you should approach horizontal. There's no problem like this here. I mean, this 3x squared plus 2 is never 0, so you don't have a problem in the denominator. That's another rational function. You have a problem in the denominator when x is equal to 1, or when x is equal to cube root of 1. Then you have 0 here. So again, you have a problem. That point is okay. Let's continue with functions and graphs. We went before. Okay, now that's a general classification. Algebraic function is one family of functions. It's obtained from polynomial functions by adding, subtracting, multiplying, and dividing. When you divide, it should not be 0, of course. And taking roots, okay, like 1 over 2, 1 over 3. So algebraic functions are obtained polynomials or rational functions. So these we call algebraic functions. Now there's another family which called trigonometric function. These are obtained from sine and cosine function by addition, subtraction, multiplying, and division, or taking roots. Now there's exponential functions. We will see that separately. You know from your high school knowledge, it's a function like this: f of x is equal to a power x, where a is greater than 1, and real constant. Then you have logarithmic functions. We will see that later on. And then we have transcendental functions. These functions include trigonometric, exponential, logarithmic, and many other functions. If you look at your syllabus, you will see that toward the end of the semester they are going to study transcendental functions. So this is sort of a more general classification. Now let's look at some properties of functions. Suppose a function as is defined on an interval, let's call this I, interval I, and x1 and x2 be two distinct points in I. Right? Is f of x2 is greater than f of x1, whenever x1 is less than x2, then we say that f is increasing because as you increase x, the function value increases too. Okay? So we say that f is increasing on I. If f of x2 is less than x1, whenever x1 is less than x2, then we say that f is decreasing on I. As you can see, as we increase x from x1 to x2, the function decreases. So you can have increasing and decreasing functions. Sometimes certain functions increases in some intervals and decreases in some intervals. So it's important to know these if we try to graph the function. Another property is we call f of x an even function if f of minus is equal to f of x. An odd function if f of minus x is equal to minus x. Now, even function is symmetric about y-axis. Of course, in order to have an even function must be defined on both x and minus x. And if for odd function, symmetric about the origin. Okay, let's look at this now. Okay, this function is symmetric about the origin as you symmetric about y-axis as you can see. Y is equal to x squared. So that's symmetric about x-axis, and as you can see, it's an even function. Y is the same for x and minus x. So y is equal to x squared is a good example of an even function. Now let's look at this function. Y is equal to x cubed. Now when, as you can see, for x and minus x, you have for xy, for minus x, you have minus y. So that's an odd function and symmetric about the origin. Just a minute. Now, what are the intervals where these functions are increasing or decreasing? As you can see, in portion for x less than 0, the function is decreases. The function value goes down to 0. Now, in this portion, the function increases. So y is equal to x squared decreases on minus infinity 0 and increases on 0 infinity interval. Now, if you look at this function, this is always increasing. So y is equal to x cubed always increases in the set of real numbers between minus infinity and plus infinity. Okay, let's look at these functions first. We have y is equal to x squared here. Let's add 1 to this, and that's y is equal to x squared plus 1 is the red one. It's still symmetric. We added something to this function. Before it was symmetric y-axis, and it's still symmetric. Okay, so symmetry is not disturbed here when you add 1. Let's look at the line. This is symmetric about origin. Y is equal to x. Symmetric about origin. That's an odd function. But when you add 1, it's no longer symmetric about the origin. So it's not an odd function anymore. Okay, let's continue. Two variables y and x are proportional. One is always a constant multiple of the other. So y is equal to k times x is shows you the proportionality. Y is proportional to k. K is a real number. Okay? Now, this is the equation of the line which passes through the origin. So, because when x is 0, y is 0 also. So these lines passes through the origin, and as k changes, we have different lines. Here we start with y is equal to 1 over 2x. So slope is 1 over 2. That's y is equal to x. Y is equal to x. And when it's minus 3, you have this line. Minus 1, you have 9. So when k is equal to 0, you have the horizontal line. So you can start from the horizontal line when m is equal to 0, that's the horizontal line. But when you change the slope, you go around like this. Now let's look at these functions in terms of evenness, increasing or decreasing. Y is equal to the square root of x is not an even function because it's not defined for negative numbers. There's nothing we can do here. And it's not an odd function, and for the same reason. And this function is increasing, increases as x increases. Now let's look at this one. Y is equal to cube of x. Okay, this function is symmetric about the origin. Because when x is 1, or let's say x is 8, so y is equal to 2. When x is equal to minus 8, y is minus 2. So it's symmetric about the origin. Let's look at okay, let me just check my sound levels. The sound level is 100, but maybe I should get close to the. Can you hear my sound now clearly? Okay, now let's continue. Y is equal to x cubed over 2 is, this is not defined for negative numbers because what you do here, you take the x cubed and take the square root. So negative numbers is not included in the domain. So that's an increasing function. It's neither odd nor even. Now when you look at y is equal to x squared over 3, now this is defined for all real numbers. And as you can see, this is symmetric about the y-axis. That's an even function. For instance, if x equals 8, then y is equal to 4. If x is equal to minus 8 here, then y is again 4 because the cube root of minus 8 is minus 2, it squares 4 again. So that's symmetric about y-axis. As you can see, it increases, this function increases between 0 and infinity and decreases between minus infinity. These are a couple of examples for functions. graphs of functions. Now, as you can see, when x is equal to 4, this function crosses the x-axis. Now, before, when x is less than 4, this is positive, but this term is negative. So you are negative if x is less than 4. X is greater than 4, both are positive, so you have positive value. So you count from negative values, cross the x-axis at 4, and then continue. For negative values of x, that's negative, and that's negative. You are still positive until x is equal to 0. Okay? When x is equal to 0, of course, your function value is 0. If you are greater than 0, of course, until 4 you are negative. When you are less than 0, you are. If you look at this function, that's 3 over 4x squared minus 1 to the power 4. Now that's about y-axis. It's obvious. If you put minus x here, plus here, it doesn't make a difference. Your value is the same. So that's symmetric about y-axis. When x is when minus 1, you have 0. It's obvious. Between minus 1 and plus 1, this is negative, but we take the negative cube root, that's negative, but you take the square again. So you are positive. Actually, you are always positive. And you can say similar. That function has two zeros. X0 is where it crosses the x-axis. X is equal to 1, it crosses the x-axis, or tangent. And you can see between 0 and 1, this is positive. Okay? You take when x is between 0 and this is negative. Inside is negative. However, you take 50 root, then you take this square, so this is always positive. So, when you're positive, that's positive. So you are here. When x is negative, this is always positive, as we said. You are on the negative side. And when x is equal to 1, that's 0. If x is greater than 1, you're again positive. These are some functions and their graphs. You have here the graph of sine function and the graph of cosine function. We are going to treat them separately later on, so I'm going to. These are exponential functions. 2 to the x, 3 to the 10 to the x, and these have negative powers. 10 to the minus x, and that's how they behave. We are going to see such functions in more detail. Same is true logarithm functions. Replace, as I said, at the end of the semester, last chapter, we are going to study transcendental functions, and there we are going to see logarithm functions and exponential functions. Okay, let's continue. Now we can create functions from known functions by doing what? We can scale the functions and we can combine the functions. Now we are going to see these. Now combining functions, we can first do algebraic operations on the functions to create new functions. Suppose you have f of x and g of x functions. The sum of these can be expressed as another function. It's f plus g of x, which is defined as f of x plus g. So by adding two functions, you get another function. Or by subtraction g from f, you get another function. That's the definition of it. Or by multiplying f of g, that's f of x times g of x, you get another function. And by dividing f by g, you get another function. Okay, but there is one restriction though. What's the domain of this combined functions? Well, domain of them should be the intersection of the domain of f and domain of g. Otherwise, you cannot make these definitions. So for these first three functions, addition, subtraction, and multiplication, the domain of these functions is the intersection of p and g. If there is no points in the intersection, then you can find these functions. Now for this function, it's again the intersection dg, but you exclude the points where g of x is 0 because this is not a real number. So when you create new function by using algebraic operations on functions, you should be careful about the intersection of the domains. Okay, let's give a break of 9 minutes. My watch is 9:51. We will convene at 10 o'clock to study.